It's the moment you've been waiting for, or the video that explains the solutions to our practice scientific notation questions. I'm going to take my time, but I don't think this one's going to take a ton of time to work through the solutions with you guys. Because if you've probably found, while scientific notation may be slightly new to you, the arithmetic itself isn't necessarily that complicated, but you may find sometimes it can be a little tedious. And so the hope is that by exposing us to scientific notation kind of early on, we can make it so it doesn't seem tedious later in our lives. It just seems kind of automatic. And eventually we're going to get to a stage where we just look at a number like this. We don't need to expand it to get a sense of how big it is. 10 to the power of 8. I look at that and I'm like, that's 100 million kilometers. And then I look at this number. I actually look at the times 10 to the power of before I look at this, because that tells me more about how far, say, the Space Shuttle Discovery traveled than this does. This is kind of irrelevant almost. If it was 3 or if it was 1, well, I'm still talking about hundreds of millions of kilometers. And that gives me an idea about the magnitude. All right. So with that aside, we'll start with some nice, simple scientific notation. So we have 2.69 times 10 to the power of 2. So what does that mean? That means 2.69 times 10 times 10, or 10, or 100. And there's a rule when you multiply by powers of 10, or when you multiply by either 10, 100, 1,000, that you just move the decimal point to the right the number of zeros you have. And it turns out. And if you didn't have a decimal to begin with, you would just add those zeros to the end. So that means that the length of the Titanic was 269, but we're not done until we gave it units, and the units were meters. And it's good to take a second to ask, does that make sense? What if, did I need an extra zero, or maybe the decimal place should have gone over here? And you can think to yourself, well, it's probably not 26.9 meters. That's less than a 100-meter dash. It's like a third of it. And it's like maybe, I don't know, length of Fraser Academy or something like that. Probably a little small for the Titanic, which we know is big. And if you add an extra zero, then you're in the thousands of meters territory, and that really measures kilometers. So there's ways to take a second to just check to make sure that is an intuitive number to you. All right, we can do a similar thing with the volume of the iceberg. So take this 1.91, and our goal is to move the decimal place 8 units to the right. After the first 2, we're kind of out of digits, but we're going to continue to shift it 3, 4, 5, 6, 7, 8, and we're going to add little zeros on top of each of those little humps there. Inverted humps, if you like. All right. And I like to try to put little commas every 3 digits. Now, I was actually counting from the right when I was putting those 3 in there. And that's a convention we use for numbers that are bigger than 0, or on the left-hand side of the decimal. So a lot of people actually also use spaces. And to be honest, actually, that is preferred. This is actually a habit of mine, because you can't really do this with decimals in the same way. It gets kind of ugly and not preferred. All right, so, and the units were liters. We measured liters. That's how many liters, how much space the iceberg took up. So you can picture 191 million like Nalgene's, or like water bottles, right? That's a typical water bottle. You can imagine 191 million of these guys. That's about how big the iceberg that hit was. So pretty big. All right, we're going to continue this along. So I'm going to write our number here, and actually what I'm not going to do in this case is write the decimal place. I'm just going to remember that the decimal place was here. I'm going to move it once, twice, thrice. 4, 5, 6, 7, 8. And I'm just going to fill in those spaces with zeros. 1, 2, 3, 4, 5 extra zeros. And that's in units of kilometers. Okay. And Spencer was asking about, or I can't remember actually if it was Spencer or Cam, who was asking if maybe I made a mistake with these units, because it seems like travel more kilometers in, like more than 1 kilometer per second, which actually might be true. It's been actually a few years since I created these questions. So I can't remember if this was like an interesting fact, because things in space can travel very fast, or if this is actually a mistake. But anyway, we'll get to that. Number of missions, this is very simple. 3.9 times 10 to the 1, well, that's actually, just move the decimal place over 1, and it's 39. 39, oh, and the units are missions. It's kind of a funny unit. And as we saw today in class, we can have weird, like non-metric units, and it's still fruitful to think about what are we measuring. Every number needs a measurement, even if it's not like something you measure with a ruler. Time spent in space. Okay, so I'm going to do the same thing I did up here. So rather than write the value twice, like over here, partly because I feel kind of lazy. Lazy's not being fair to myself. I've been working for a long time, and I just recorded an hour-long video for my math 10s. Anyways, so I'm going to move this guy decimal over 7 units, so once, twice, thrice, 4 times, 5, 6, 7. So I'm just going to add zeros on top of there. And that's in units of seconds. And so that's about 31 million seconds. Oh, that sounds significant somehow. Yeah, come on in. I feel like that's a significant number of seconds. Like, is that maybe the number of seconds in a month? I don't know. Anyways, there you have it. Yeah. Okay, so this one is a big, gross wall of text. So we're just going to read through it carefully. All right. So this is a funny word. It's pronounced Escherichia coli, which, because nobody ever wants to pronounce it, we just call it E. coli, which you've probably heard of. It is a gut bacteria. Lives in our bodies. And is a model organism. We use it for genetic engineering. And they're typically about 2.0 times 10 to the negative 6 meters long. Okay, I'm going to use a different color highlighter for the next one because we used yellow for this bacteria. And then we have this thing, it's called Enterobacteriophage T4. It's got the word bacteria in its name, but it's because it kind of targets bacteria. This is actually a virus. All right, E. coli is a bacteria. Now, if you're taking, say, Biology 11 this semester, you're going to learn about the difference between bacteria and viruses. Maybe you already know. And so they target E. coli, but they're like 1,000th of the size. So you can imagine like tiny little ants attacking us. Lots of them. All right, and so they're about 2.0 times 10 to the negative 9 meters long. And if you notice, if you compare these two numbers, you'll notice there's like a difference of a power of 3 on 10. And you might remember that 10 to the power of 3 is 1,000. And that's where that 1,000th number comes from. Anyways, so our Enterobacteriophage T4 inject their DNA strand into the bacteria. And that's a 1.69 times 10 to the 5 base pair DNA strand. And that's how long the DNA strand is. And it gets mixed in with the bacteria's 4.6 times 10 to the 6 base pair DNA strand. And we see the length of DNA is measured in units of base pair. So that actually seems pretty relevant. And that means pairs of, well, you might have heard of A's, T's, G's, and C's if you learned about DNA or genetics in grade 9 at all, in grade 9 science. So that's what we're talking about. We're talking about base pairs. All right, so enough of that. Let's see if we can turn this into non-scientific notation. We're going to expand it. So I'm going to start with writing 2.0. And where am I going to write it? We'll write it over here, 2.0. Now, I'm going to move the decimal to the left because it is a negative exponent. You can think of it going in the negative direction on an axis. That's the way I think of it. Because if you have an x and a y axis, you have a negative x value over here and the positive x is there. So the negatives move to there. Okay, so I'm going to move it once, twice, 3, 4, 5, 6. And that's where my new decimal place is going to be. I'll just add zeros in there. Okay, so the length of the E. coli is 0.123450 zeros, 20. And I'm actually including that extra zero for a reason, but that reason has to do with something called significant figures, which we haven't talked about yet. So if you just wrote the value like this, that is actually fine. It means you understand what we're doing now, and your understanding will just get refined as we learn new things. And the units for the length is going to be in meters. That's how many meters. And does it make sense that we have such a small number of meters for bacteria? Well, sure. There are billions of them living inside us. So they got to be pretty small, right? I think it might have been an underestimate. There might be trillions in us. Anyways, let's move along. So now we're going to talk about the length of Enterobacteriophage, T4. All right, so that's we'll still at that 2.0, and we'll shift that decimal place once, twice, thrice, 4, 5, 6, 7, 8, 9. Put the decimal place there, and we'll have 1, 2, 3, 4, 5, 6, 7, 8 zeros to the left of the 2. 0.1, 2, 3, 4, 5, 6, 7, 8, 2, 0, and also in units of meters. Oops. And then we want to know what the length of the Escherichia coli genome is. And length of DNA is measured in base pairs. It tells us how much information is packed inside your genome. That's another way to measure length. Kind of a funny way to measure length, but it's a way that biochemists prefer. So take it up with them. Which I guess means, yeah, I guess I'm not a biochemist. All right. So in the E. coli genome, where is that? The E. coli is a bacteria. So where do we talk about a bacteria's genome? Oh, this is the bacteria's genome here. Bacteria's, that's the E. coli. E. coli. Length of its genome. So what we're going to do here is we're going to write, it looks like we're going to get bigger, so we're going to move to the right this time. So 4, 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And when you get comfortable with this stuff, and the units are base pairs, you actually don't have to necessarily draw that line like this all the time. You're going to get good at kind of counting, imagining drawing that line in your head, and you're just drawing a number of zeros that are equivalent to it as you count. So we'll try that for the next one, okay? And I'll just be modeling what you're going to do when you're comfortable with this. And who knows, maybe even by question 3, you're already comfortable with this idea. So now we're going to write the length of the Enterobacteria phage T4 genome, which looks like it's 1.69 times 10 to the 5 base pairs. So it's 1, 6, 9, and so I've got 2. So really what I'm doing is counting the spaces to the right of that decimal that was here. And there should be 5 in total. Now there's 2, so I need 1, 2, 3 more. And that's kind of how you'll be dealing with expanding scientific notation when you're comfortable. And to be honest, once you're really comfortable with scientific notation, actually you only are going to want this. And that's kind of the end goal. Not necessarily for our course, but if you're going to pursue science, you're not going to get far without not only knowing how to use this, but kind of being comfortable and conversant with it. Taking a number like this and having it make sense to you. Not having to expand it to know that it's big or it's small, or how big or how small. Is it bigger than this? Is it bigger than that? How much bigger? Is it significantly bigger or trivially bigger? So that's those are kind of questions that you will learn to get comfortable with over time. All right, moving on. Oh, the Large Hadron Collider. Oh, another gross wall of text. It accelerates protons, and the protons have a mass, and that mass is, well, it turns out very, very, very small. And the speeds that it accelerates protons to is 2.998 times 10 to negative 8, pardon me, 10 to positive 8 meters per second, which is almost the speed of light. I can't remember how many nines, but it's something like 99.99 something percent of the speed of light. It's very, very close. And they get and it would seem like they keep gaining energy, but because of their tiny mass, their kinetic energy is still so small, even though the velocity is quite great, which is fascinating. A joule is not that bit much energy. But even getting smoked by one of these traveling the speed of light, it's going to hit you with a very small amount of energy. It's like oh god, I don't want to do a conversion right now. I was going to try and convert it to food energy, but you know what? It's been a long enough day. Let's move on here. Well, okay, so we're smashing stuff together, fine. In LHC, a proton takes not very many seconds to run a full lap. And it has this track, and the track is 2.7 times 10 to the 4 meters. And I used pink twice. What a guy. I didn't mean to. How about green? All right, we haven't used... Wait, we did use green. I can't be out of colors, can I? I have so many colors. Got lavender. 3 times 10 to the 14 collisions. All right, so it looks like we got lots of values. And we got to start with the mass of the proton. So we know that mass, as we talked about on the front page, is measured in kilograms, which I didn't fill in here, but you guys did, hopefully. So that means that we're going to be talking about kilograms here. So we look for where we express something in kilograms. Oh, okay, this is the mass of a proton. It is painfully small. All right, so I'm going to write, so what I'm going to do is I'm going to write the 1, 6, 7 here, and I'm going to count how many times I have to move once, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and I know you may have done this and felt like this was absurd, and in a way, that was kind of the point. The point is that in science, we encounter really, really, really big numbers and really, really, really small numbers. Often. Like a proton, for crying out loud. We use that all the time. And this can't be the way that we do business. This is insane. That's why we really want to feel comfortable with this. And, like I said, don't feel like you are obligated to be able to look at this and make sense of it right now. That's something that's going to come with time. What you are obligated to know how to do right now is be able to just convert between them. And that's like stage 1. All right. So same thing here, but it's positive exponent, so we're going to be moving to the right. So decimal's going to move to the right, so I'm going to say 1, 2, 3 times. It's already moved. And we're going to move another 5, so that's going to be 5 zeros. And then the decimal would be there, but I don't need to write a decimal when it's a positive number. And I like to put commas in there as a bad habit. So it's like 299 million-ish. Oh, and the units are meters per second, which isn't a base unit. It's a measure of speed. It's a combination of 2 base units. Meters, which is distance or length, and seconds for time. All right. How much energy does a proton have at full speed? Well, 1.12 times 10 to the negative 6 joules. Okay, so that means we're going to move the decimal to the left. This is 1, 1, 2, and we're going to move that decimal once, twice, 3, 4, 5, 6. So it'll be a decimal there. And so it'll be 1, 2, 3, 4, 5. And units of joules. All right, where are we at here? Number of collisions in the first 3 years. Okay, so they had an awful lot of collisions. All right, so it's 3, and we're just going to take the decimal place that would be right to the right of that 3. We're going to move it 14 units to the right, and I'm kind of a jerk. I didn't really leave you enough space. So you're going to write your zeros real small. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And what are the units? These units are collisions. In case you were wondering. All right, and the time it takes for a proton to make a full loop, well, it's not going to take very long at all. The 8.89. And again, I don't want to write the decimal because I'm going to, rather than do this in a second earlier step and then rewrite the number, I'm just going to try and write it here. So what I'm going to model is having a decimal here and shifting it once, twice, 3, 4, 5 times and putting the decimal there. And that is units of seconds, which I can just use the symbol S. And the length of the track is 2.7 times 10 to the negative 4 meters as a circle. So let's think about how big that is. So that must be pretty big. And it is. If you know anything about the LHC, it goes through, what, 3 different countries, I believe? Once, twice, 3, 4. Once, twice, 3, 4. Meters. And that's like 27,000 meters, which is about 27 kilometers, which is a big track. And there's a little picture of it. Swell. All right, let's move on. Okay. Lots of text here. Oh, there's my other color that I really needed earlier. All right, so what do we got? Water molecule has a mass of, all right, gross. And it is composed of 2 hydrogen atoms, covalently bound to 1 oxygen atom. Not a surprise, I'm sure, to you guys. And the distance of the bond between an oxygen and a hydrogen atom is this long. And the angle between the 2 bonds is always, interestingly, is fixed, turns out, with water. And water is always bent in this way. There's always an angle, and that angle is never not this many degrees, which is kind of wild. That means all water molecules look identical. And they do. All right. So a negative exponent. So if we want to expand this, we've got to move this decimal to the right. And by right, I mean left, which is the opposite of right. So we're going to move it to the left 23 times. So once, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Bang. There we go. There's a dot. Called the dot. Decimal. All right. And we've got to put all these zeros in. And I promise I'm not going to make you do this all the time. Because I care about how you spend your time, and I don't want you to do useless things. The length or distance of the bond is this many. Again, is a very small value. So 9, 4. That's not a 5. That's a different number. 5, 9, 4. And we're going to move this decimal place to the left. 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Decimal. 3, 4, 5, 6, 7, 8, 9, 10. And units of meters. And the angle is, interestingly, so we're going to move this decimal to the right once, twice. Actually, we get 109.5, and the units are degrees. So I think if I just put the symbol, it would be a little misleading, so I'm just going to write degrees. I'll write a little dot there like that, which is still not clear. All right, moving on. So let's take a look here. So here, likely we get to write a little less. We're doing the same amount of counting. All right, so we'll read through this question here. So a mole is a peculiar number that we use sometimes in chemistry. And it's a way of grouping, okay. A pair is 2 things, a dozen is 12. A mole is this number of things. And it turns out we use a mole to measure out, like, if we want, say, a handful of, say, water molecules or a handful of carbon atoms. These things are all very, very small, as we see, you know? And so if we want to get them into like a usable amount, like a tangible amount I can hold in my hand, I multiply, then I'd have this many, say, water molecules, and that would be about a handful. It's actually a little less in the water's case, because water is extra small. But that's kind of what we use it for. Ooh, don't worry, that'll be unpacked later. We don't need to understand it. We just need to convert this into a unit and kind of get familiar with it. So we're going to demystify the mole slowly. We're going to see it pop up here and there when we don't really need to understand it, and then maybe we'll understand it later. So we look at this number and we see the decimal place is here, and we're going to shift it to the left until we can construct a number that is between 1 and 10. So 1, 2. Did I already screw up? Yes, I did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, and we'll put the decimal there. So we could say that is 6.022. Now, can I write a 0 as well? Do I write all the zeros? That's a good question if you thought about that. If you didn't, that's no big deal. Times 10 to the power of, we got to count how many times we shifted. We shifted 23 times. And a mole is, what are the units? Units are things. That's what a mole is. It's a certain number of things. So if you have a mole of dollars, you have that many dollars. And nobody, in case you were wondering, has that many dollars. All right. So we'll come back to the mole, or the mole will come back to us. All right. Question 7. So radiation that is emitted from a cesium atom, it's used to define how long a second is. That's how we define how long a second is by the radiation of a cesium-133 atom. Isn't that wild? Yes is the answer, in case you're wondering. Yes, it is wild. All right, moving on. All right, so we got a second is equivalent to, wow, that many periods of radiation. What is that? That is counting 9,192,631,770 periods of radiation. And that's how we define a second. And if that isn't pleasing to you, if that isn't like delightfully crazy, man, I think you may be in the wrong course. Because chemistry is often about, like, I hope that you're going to find some of the pleasures in chemistry are just the wild ways we learn to use chemical truths. All right, anyways, let's keep reading. And a cesium-133 atom has a mass of 133 AMUs. That's what that number there meant. And you might have remembered learning about this way of writing isotopes in grade 10. It's a mass of 133 AMUs. And an AMU is a weird, dumb unit. It's also known as an atomic mass unit. That's what AMU stands for. An atomic mass unit is the kind of unit you would expect a bunch of uninspired chemists to come up with. And that's the same thing as a certain number of grams. And those are equivalent. Actually, we have two equivalences here. So this inspires me to maybe write a couple of conversion questions that involve converting mass of AMUs to grams and atoms into, or seconds into periods later when we talk about unit conversions, because I think this is extra special. And as you can tell, I wrote this a few years ago, so it's like I'm reading it for the first time, although I've used this sheet several times. All right, so what are we doing here? We're turning all this into scientific notation. So first, number of periods of radiation in a second. So we're going to take this decimal place here, and we're going to shift it 1, 2, 3, 4, 5, 6, 7, 8, 9 times to the left. And so I would write that as 9.19, and I would actually keep all of those decimals. And if you didn't, that's actually okay for now. But I'm doing this because I'm assuming that at least one of you watching this is doing this at the end of the year, reviewing some principles. And at the end of the year, oh, what am I doing? I just kind of zoned out. I was talking, and I forgot what I was doing. And those people who have finished it all the way to the end of the year are going to understand why I left all those decimals there, because these are significant values. Anyways, times 10 to the power of, I already forgot how many I counted. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the units are periods of radiation. Okay. Mass of a cesium atom is 133 AMUs, and it's also some number of grams. We'll start with the AMUs first. Dot. Decimal there. We'll move it once, twice. That's 1.33 times 10 to the power of once, twice. AMUs, but it's a very weird, different number of grams. And it's going to be times 10 to the negative value here, because it's a very small value, smaller than 1. Smaller than 0, more importantly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Do we stop there? No, because we're trying to make a number between 1 and 10. So we go 21, and now we have 2.209, and that's a number between 1 and 10. 2.209 times 10 to the power of negative 21 grams. Did I count that right? Possibly. You know what? I think it's been a long night. If you want to double check that and prove me wrong, please do. I guarantee I will supply you with greater than or equal to 1 cookie. Oh man, so much reading. Okay. So we can't use light microscopes to look at atoms, because the shortest wavelength of light is, okay, it's this many meters. So wavelength of a visible light, that's the shortest wavelength. And atoms are much smaller than that, which is crazy. So we can't look at things that are smaller in length than light's wavelength itself, at least not using light. So the question is, how do we look at them? What a wild question to try to answer. Turns out the truth is really interesting, and we're only going to look at a slight shade of it. All right, so it's quite unlikely for light to bounce off atoms back into our eyes. So uranium atom, for example, has a radius of, uranium atom's radius is 0. And uranium is a big, chunky, fat atom. But okay, is this bigger or smaller than this? Maybe it's hard to visually see. Maybe it's easy for you. So we're going to turn them into scientific notation to compare them. And then we want to say, okay, well, if we want to look at small things, we often use electrons instead of light, because their wavelength. And when I say electrons instead of light, what I really mean is electrons instead of photons, because the light is actually made of particles called photons, or one would argue that they do. All right, electrons, because their wavelength is shorter, is this many meters long. So electron microscopes can resolve very small things, like cells and viruses. But we still, this wavelength is not long enough, or sorry, it's too long still. It kind of like waves over a lot of uranium atoms. So we have other imaging methods for looking at some large atoms. Actually, we can look at small ones too using other methods. Yeah, what a thing. All right, shortest wavelength of visible light. Shortest wavelength of visible light. We're going to just write the length there. So we're going to move it 1, 2, 3, 4, 5. When do we stop? 6, 7. We stop there because that is a number 3.80 that's in between 1 and 10. And I already forgot what I counted to. I think it was 7. 1, 2, 3, 4, 5, 6, 7. And the unit is meters. Oh, wait, but we have a small value here. It's a -7, pardon me. Now the radius of a uranium atom, how does that compare? Is it bigger? Is it smaller? So we'll count the same. 1, 2, 3. My eyes are spinning here. 4, 5, 6, 7, 8, 9, 10. So that's 1.96 times 10 to the -10 meters. So like 1,000 times smaller, or power of, or 3 orders of magnitude difference. That's how much smaller this is 1,000 times, 3 orders of magnitude, or 10 to the power of 3 times smaller. And the wavelength of an electron here. Okay, so we're going to move this guy 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so that means it's 1.12, left the decimal place here, 1.12 times 10 to the power of negative, I think it was negative 11 meters. This is actually getting not so bad. Wait, hang on, did I count right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. But in practical terms, these are too near in size to get good resolution power just using electrons, which is fine. We have plenty of time to learn about that if you're interested. These things are called electron microscopes. Okay. Lastly, we got a question about Project HARP, a High Altitude Research Project, which is one of my favorite crazy science stories. A joint effort between the U.S. and Canada to create a cannon that fires satellites from Earth into orbit. So they were going to launch things into orbit just by firepower. That was the goal. And they were trying to build something because that would make launching things into space much, much cheaper if they can figure out how to do that. All right, so it wants to... The escape velocity on Earth is about 3,600 meters per second. And the barrel is a 40-meter long, which is, I usually multiply by 3, so that's like 130 feet. And 410 millimeters wide, which is like this. What is that? That's 41 centimeters. You can picture that, like bigger than a ruler. That's the barrel of the cannon that they built. And it cost $10 million to build. This is just hilarious, wild stuff. There's a tragic end to the man who created this, and not in the way that you might expect. So there's some research for you if you're interested, or just come and ask me about it during Flex when I'm not busy, because I would love to talk about it. I think it's hilarious. All right, we're just going to turn this into decimals, and then we're going to move 1, 2. Did we stop there? No, that's 36. We need to make a number in between 1 and 10, so we move one more to 3.6. So it's 3.6 times 10 to the power of 2. Nope, 3. And the units are meters per second. That's how fast the satellites would have to leave. They never did, by the way. This never worked. All right. Not that it never will. Barrel, we'll just move the decimal over once. It's going to give us 4 times 10 power of 1 meters, which is also like saying 4 times 10 meters, which is fine, way to write it. But usually people actually write the 1. Unlike math, actually, where you don't write when you have a power of 1. You may be getting that habit a lot. With scientific notation, actually, we do denote it just to actually indicate to people that we're using scientific notation, that we're not just writing 4 times 10, some unresolved problem. It's a way of just signifying that we have scientific notations, even if it's a value of 1. All right, width of a barrel, so 1 twice, so it's 4.10. All right, let's just keep a convention here. We're not counting our zeros right now. Times 10 to the power of 1, 2. And they're units of millimeters. And the project was 1, 2, 3, 4, 5, 6, 7. It'd be 1 times 10 to the $7, which is $10 million. All right, well, it took way longer than I expected. I actually kind of got into rereading some of the questions that I wrote. I guess I'm my own biggest fan. Lame. Anyways, let me know if you guys have any questions about any of the reasoning that I used there, and I'd be happy to work through that with you during Flex or after school or something like that. But just let me know.